Okay, we're going to start our last topic for the course, and we're going to look at what we call quarks. And where quarks come from is we think that leptons are pretty small, so we looked at things like electrons and things like that. So we thought those are probably the fundamental particles, and hadrons are really big, like protons and neutrons. So we thought that maybe those are just made up of other things. But in the 1960s, a couple of guys said that there's actually things that make up the hadrons and these particles. So they're basically what they're saying is there's particles within these particles that actually make these up, and they called them quarks. So what happened is they basically said that everything, all hadrons, could actually be made up with quarks. So they basically came up with the idea of just 3 quarks were needed, and they said that the up quark had a positive 2/3 elementary charge, and they used the symbol for U for up, and they had a down quark that said it was a negative 1/3 charge, and they used the symbol for D. This whole idea seemed pretty strange to most physicists, and they never kind of thought that it was possible to have a fraction of a charge. But in the later 60s, they were making a high particle accelerator, and they were shooting electrons and protons. And what they found is that the electrons actually deflected around the proton in weird patterns, and they weren't just evenly spread out. They actually got things to change depending on sort of this third model. So they saw if an electron was near the down quark, which was negative, they actually got a little bit of repulsion, so the electron curved away. If it was near an up quark and was really close, right, because those are positive, so you can see there's lots of attraction, the electron curves closer, and so on. So they got some weird things going on in terms of the deflection, so they actually thought this quark model was actually true. So the quark model has actually been built up to actually have 6 quarks and anti-quarks, but we've actually we only narrowed down in terms of just the first generation. So in terms of what you have to use for the diploma, you only have to worry about the first level. So we think of as a proton as sort of being quarks and a down quark. So we've got these 3 particles making up the one proton. And what happens is all hadrons, all of these particles can be built from 2 or 3 of these quarks depending on what the particle is. The exception is a theta actually is built up of 5, which is kind of weird. But most particles are typically made up of 3, and a few of them are of 2. So the second generation and third generation, the idea is we sort of have like a proton. It's made up of these 3 quarks. Within each of those quarks, it's made up of 3 inside of that, and then inside of those, there's also more of them. So that's how they get the first, second, third generation idea. So let's use up and down quarks to figure out what a proton and a neutron would be made out of. So a proton is, we know it has a charge of positive 1, so we know that to get a positive 1 only using 2/3 and negative 1/3, if we do the math, we know we'd have to have two positive 2/3 and 1 negative 1/3. So if we do the math on that, you can see we get positive 4/3 minus 1/3, which would end up being 3/3, which would be the same thing as positive 1. So our proton then would be basically built up of 2 up quarks and a down. A neutron is another hadron, so we know that it's neutral, so we got to do the same thing. What would it be made up to get something neutral? So in this case, if we have positive 2/3 and 2 negative 1/3, that would give us a 0, which is neutral. So then a neutron is an up quark and 2 downs. And we can actually do the same process for everything. So any of the other hadrons can all be broken down into up and down quarks as well, and so on. So we can actually use this logic because we know that when we do beta positive and beta negative decay, it's actually just a proton or a neutron changing into something else. So we can actually use this sort of logic to describe this. So we know that in beta negative decay, we start with a neutron and it decays into a proton, and then we get our electron shooting out of it plus our antineutrino. So our beta particle is that electron. So if we actually do this in terms of quarks, we see that our neutron, which started up as an up and 2 downs, changes into a proton, which is 2 ups and 1 down, And if we actually do that, if we do the comparison, you can see we went from a down to an up. So we went from -1 to positive 2/3. So we've actually made a difference of 1 whole charge. So that's why the electron has to be generated to balance the charge. We have to get our net charge of 0. We got to get our net change. We started with a neutron. We still better end up with a 0. So even though using the quark idea, we change one of the quarks to go from a proton to a neutron, that's why the electron also has to be created to balance things out. And in beta positive, it's just the opposite. We start with a proton, and it converts into a neutron and a positron. So if we do this, you can see the same sort of thing works out the same. So our proton was 2 ups and a down. Our neutron is 1 up and 2 downs. So we'd have, in this case, we're going from a positive 1 charge to a 0. So we end up having to have that extra positive 1 charge to make up for it. So the same sort of idea. We do a down quark of -1/3, and we subtract a positive 2/3, that ends up giving us that net charge of 1. So we still end up with a overall charge of 0, which works. And we still have our neutrino. I didn't put that on there, but that would also exist. So the idea is with quarks, it kind of helps explain how the conversions work and to make sure we're still following the conservation of charge. We are now done Physics 30, so there's no more lessons, nothing to do, so we're pretty much done except just a small thing called the diploma exam. And that's it.